And I will, after discussing ergodic theory and discussing some algebraic geometry, I want to relate it to now and discuss measures on variety, in particular ergodic theory or dynamics of such things. So just a measure on a variety is sort of very arbitrary. We know the theory. This is basically Riesz theorem. We know all measures in some sense. What is interesting for us now is the dynamics of such. For example, if I have an algebraic group acting on an algebraic variety and a measure on that variety, what would be the structure of the stabilizer of that measure? So let me put this on the table. So assume we have this algebraic action. Again, more words. By this I mean G is an algebraic group, V is an algebraic variety, G is an affine algebraic group, V is an algebraic variety, and there is an algebraic action here. So the map that defines the action is algebraic. And we know also, by the way, in this lecture and from now on, we know that on algebraic varieties we have two topologies. There's the Riesz topology and the Hausdorff topology. When I'm discussing topological terms or Borel terms, it's always back to the Hausdorff topology, unless I will add the sign Z or Zariski denoting that this is the Riesz topology. Okay? So the default topology is the Hausdorff now. And on V, and we know that V is a nice topological space by itself, and there is a nice space of measures, in particular probability measures on V. And pick one. Mu, probability measure on V. And I'm concerned now in this theorem about the stabilizer in G. So G does act on V, does act also on the probability measures on V by just pushing forward. Whenever I have any measure mu, I can take G star of mu, which is a new measure, and it is defined as follows. It measures the set A as mu would measure G inverse A. This is a standard push forward, and most of the time I will omit this lower star sign, since I identified G with a group of automorphisms of this measure. So G does act here, and I can ask what is the stabilizer in G of this arbitrary measure mu. In this discussion, let me call it L. So L would be the stabilizer of the measure, and the statement I want the theorem trying to prove now is that L is almost algebraic. Almost algebraic means it has a normal algebraic subgroup such that the quotient by this algebraic subgroup is compact. So it is algebraic by compact. So there exists H, normal in L, which is compact in L. Algebraic, let me repeat again, normal subgroup. So this already gives a lot of restrictions about the structure of L, but moreover, it so happens that mu is actually supported on the fixed point of H. So by V to the power of N, or superscript H, I mean the H fixed point in V. G act on V, H act on V, some points are fixed, and the measure of the fixed point is everything, is one. Our measures of probability measures, this is everything.
I mean, I don't understand, I don't see what is the general background here of this theorem, because when you say an algebra algebraic group acting on an algebraic variety and so on, then naturally you would say, I would say it's over an algebraically closed field or a field with this.
So as I
With
said,
this absolute value, but this absolute value is still something that may be quite abstract, not related to reals. And then you are saying that the
so this
N
theorem.
over H is co-compact, and so
Yes, we have two topologies, and co-compactness of L mod H.
H topology.
This is in the house of topology. Yes, as I said, I didn't write it down. Sorry. When I use topological terms, unless otherwise said, this is with respect to the house of topology.
Great. And then as an L, the stabilizer of measure L under G, well,
This is completely algebraic definition, right?
say it again.
There is no topology in this definition of L a priori.
Well, this is the subgroup of G.
Then,
And then the natural would be the subspace topology. Right?
So yeah, there are two topologies on L,
Yes.
coming from the two topologies on G, and since L itself is not algebraic, mostly I will think of it as in the house of topology, and it is standard that stabilizers of measures are closed.
Oh.
Closed for the house of topology.
Close in G.
Closed in G for the house of topology.
Which is, I don't think it is trivial.
No, I'm not saying it is triviality, but it is, well, it follows from the fact that G does act on the space of probability measures continuously with respect to some weak star topology. Right? If we did take a compact model for V, this was clear. I mean, maybe V itself is locally compact, but, okay, compactify it. The one part of
There is a general question to a theorem like this, namely, certainly, if you consider algebraic varieties and complex algebraic varieties, it is quite natural to look at probability measures on sets there. But if you look in an abstract algebraic setting,
No, I'm not looking at an abstract algebraic setting. My setting here, as of yesterday, is that sorry for not saying it. I think this was it was in my mind from yesterday, so I thought it was in yours as well. We fix K algebraically closed and complete
oh right, yes, yes.
with respect to some given fixed absolute value. But
Okay.
if any of you find this a bit abstract, think C. C is good. And many of the things I'm saying actually are correct also for the reals and for the periodics. But again, this is just a setting that we did not discuss. So now everything makes sense? So this is the theorem. And how one goes and prove it, this will be the subject of our discussion now. Actually, I will prove a more general thing by changing the point of view. Instead of, in my mind here, I fix the algebraic action, I'm varying mu, hence varying the stabilizers, and then I'm trying to understand how the stabilizers, the various stabilizers look like as subgroups of G. This is what is going on here, but what I will do now is inverting the situation. Let's fix any group, L in G, and try to analyze all measures for all actions that are fixed by this L. This would be like in Galois theory. Sometimes you fix the group and you want the look at field. Well, forget analogies. Let's write the proposition. In the spirit of what I said. So we fix G. Algebraic group. A fine algebraic group. We fix M. not necessarily algebraic. Let me emphasize this. And then
SG comes goes for subgroup.
sorry.
SG, this abbreviation. Subgroup? Yes.
Subgroup, yes. So, then my claim is that this H, which is normal, it is not in L itself, but it is in, there's a recent closure of L. Normal algebraic. H is an algebraic subgroup. Such that L has a trade contact. This is how, of course, image in the quotient, mod H. So H is normal in, there's a recent closure of L, so I can take the quotient, and in the quotient I can push down L into a subgroup here, and well, it may not be closed a priori, but the closure is compact. And now vary V. For every algebraic action, G on V, and for every mu, implication, if mu is a L fixed probability measure, then mu is supported on the H fixed points. So this proposition is not hard to prove, but it is quite powerful and has many applications, and I will try to explain this. Let me start by showing how it implies the theorem about stabilizers. Oh, but maybe, are there any questions about formulation? So this is about fixing L, varying V and mu. Here, we fix V and mu, and we ask about the structure of L. So, trying to prove the theorem, let's fix V, as in the theorem, and mu. And now set L to be the stabilizer in G of mu. Again, as in the formulation of theorem. Now take that L, let H be as in the proposition. With respect to L as the setting, as the notation suggest, sorry, as the notation suggests. So one thing we know from the proposition, this happens for every V and every mu. We know this right away. Moreover, this gives something that we didn't have a priori in the proposition. It gives that H not only H actually fixes every point in the support of mu. So certainly H fixes mu as well. In our case now, H is a subgroup. In the proposition, we didn't know that H is a subgroup of L. But in the setting that we have now, H is a subgroup of L, must fix mu. This implies that H is actually normal in L, since it's normal in its closure. The closure of L normalizes H, any sum of that closure, of that Zariski closure, normalizes H. In particular, L normalizes H. And finally, we know that L is precompact. Mod H, and it is closed. So L is compact mod H. So H is compact. Maybe a remark about that. We know that the image of an algebraic group under an algebraic homomorphism between groups is always closed. In general, the image of a group under a homomorphism need not be closed. Take the image of an irrational foliation of the torus by the H. This actually, I can think about it as, I don't know, R2, 2R2 mod C2. And I can take some ring, some embedding of the rings here, irrational embedding. The image of this here will be non-closed. Sorry, I'm not giving details, I just apply to intuition. The image of a subgroup under a homomorphism need not be closed, but if this subgroup contains the kernel, the image is closed. Of course, and this is the case here. L is closed in G, it's the stabilizer of something, and it contains the kernel H. So the image mod H is closed, and hence it must be compact.
But here you are using this L is closed, and then you said
That
how does it follow that L is closed? You say it's closed from considering some.
yeah, stabilizers of it's a general fact.
General fact, I see.
Yes, the stabilizers of measures when you are for locally compact spaces are closed. Yes, I'm using it. Because the action on the space of measures with respect to the actual topology, the Weak-Star topology, is continuous. Whenever you have continuous action, point stabilizers are closed. Okay, maybe before proving the theorem, before proving the proposition, let me give more observation and corollaries coming from this, which are very important, not trivial. Take G to be SLNC. And let's this one act on V algebraically. And take L to be SLNR. So take mu to be a probability measure on V, which is SLNR invariant. So whenever SLN acts algebraically on a variety V, so complexifying when SLNC acting on the C points, and you may want to look at, may want to consider invariant probability measures on it. Let me give you an example, maybe. SLNR acting on the affine M space linearly. Of course, this is an action of SLNC on the affine complex space, and just looking at the real points of this. And I want to put a measure on it, which is invariant under SLNR. Obviously, think of it, you can't do it unless you put the delta measure at 0, which is fixed. This is the only way one can go. So this could be, I can give you this very specific example as an exercise, but let's try the very general. Then my claim is that mu is supported on the fixed point. so this is quite powerful. And proof from the proposition, take L to be SLNR, observe that it is risky dense in G. So we are in the setting of the proposition. Let H be the group given. From the proposition, or by the proposition, and observe that H is normal in M bar, in G. G simple implies L very compact mod H implies that H cannot be trivial because L is not a compact subgroup. So H is mu VG then it's mu VH given by Fermi is everything. Okay, so this is nice. A corollary of this corollary is what is known as the Borel density theorem. Of course, by the way, I'm stating things for SLN. This is much more general. You can replace, I use simplicity. You can replace it by every simple, or actually a semi-simple group. Let gamma in SLNR be a lattice. Then gamma is a risky dense. This means at some differential C, there's a closure of gamma is everything. And this one. So Borel came with, maybe just let me hold and say a word about the history. Borel came with quite complicated move of this. You can still see it in Raghunathan's book.
But there must be some additional assumption, dimension of the lattice, because it must be specified, right? Because
No, a lattice is discrete sample.
discrete, so it can be just one-dimensional.
It is zero-dimensional. I mean,
And I mean,
The fact-
it has a Z module.
the fact that it is a lattice forces the risky density. It may come as a surprise. I mean, maybe not after the
Oh.
road we passed, but
So for instance, if you take,
it's like Z is a lattice in R, and it is risky dense,
uh-huh.
even though it is very thin in it. So this is a similar phenomenon somehow. So this was proved by Borel. Fürstenberg later on came up with a very neat argument, very dynamical argument, proving the same thing, which basically leads one, I mean, this was implicit, but one can study his argument and actually discuss measures on variety, etc. Zimmer didn't, to a great extent. What I present here is a version. It's a new proof of the same kind, slightly more general, and I think simpler. So consider the action of SLNC on a certain algebraic varieties. What will be the variety? It will be SLNC modulo the closure of gamma, this cosette space. What I need to show is that this guy here, I mean, this cosette space is just one point, right? To show the equation between this and that. No, there is a map from SLNR mod gamma. This is SLNR map, equivariant, nice map from here to there. Right? I mean, obviously, SLNR act here at this base point is fixed by now. So there is a map from this cosette space. And here you have invariant probability measure, and you can push it and get some here. But this one must be supported on the fixed points. And there is no fixed point in this cosette space unless this cosette space is just one point. Well, any question?
So you mentioned that he proved it in the book, Borel proved this in some book, in your book.
Borel proved it. I didn't read the original article. I know the proof from a book by Unatan. About lattices. Very influential book. Okay, so I discussed nice applications. I need to prove the proposition. So again, let me recall the setting of the proposition. In the setting of the proposition, I fix my universe group G, and I'm fixing any quite arbitrary subgroup of it L, but this one is fixed through the discussion, and I'm kind of trying to understand all possible actions on variety fixing probability measures. I will vary the variety and will vary the probability measure. Somehow, let me just conceptually justify a step that I will take before taking it somehow, so the proof will be clear, the strategy. Whenever I am acting on a variety, fixing some probability measure, I can disintegrate the measure and find other measures supported on specific fibers, on specific orbits. Right? Because I know that there is a nice quotient space, V mod G, I can integrate a measure mu on V with respect to this nice quotient space, this nice factor map, and get disintegrated measures supporting on specific fibers. So if I have a measure on any space, then I will have a measure on an orbit. So why not consider them first? Just measures on the orbit. These are the tools. And measures on orbits are just measures on quotient spaces, G mod H's. And of course, if I have G mod H1, and H1 is smaller than H2, and I have G mod H2, then I have a natural map here. And if I will have a measure here, which is invariant, I can push it to a measure here. So somehow this is less interesting. A more fundamental object would be a measure here than a measure here. So I would try to find a measure which is supported on G mod H for H as little as we can. And this I can do by using the Noetherian property. I will look at the collection of all H. Okay, now I'm ready to write down something which is meaningful. Proposition. Consider fix G I prime, fix L in G. Consider the collection. This is a trick that I will use over and over again. Consider the collection of subgroups H in G, algebraic subgroup, such that there exists a measure on the concept space which is L invariant. So the measure is not a part of the collection. Its existence, the existence of such is what marks a certain subgroup as a good group, and I will look at all the good groups in that form. Obviously, since G mod H, if you take a conjugate of H, the concept space G mod H is just the same. This collection is closed under conjugation. Some are with things up to conjugation that matters here, but actually I want to look at the groups themselves, because this is a collection of closed subsets of G. So the Noetherian property of the topological space, the Zariski topological space G, gives there exists a minimal. It's not a global minimum of this, but there is some minimal element H. I will denote H in that collection. Oh. And given that guy H, I can take, maybe this mu is not unique. Its existence is given here, but I can pick one. Pick mu in G mod H, this specific H, L invariant. Is this clear? Should be. And again, this is a trick to remember. I will use it over and over again. There's one step that I want to do and forgot. I want you to bear it with me by observing that I can replace G when proving the theorem, but I can assume that G is the Zariski closure of L, that L is dense. Because if this applies for the if the proposition is correct for this specific G, then it is correct for any bigger G. This will facilitate next steps. Okay, now there is a claim. It is not entirely trivial. The claim is that under this assumption that L is dense, Zariski dense in G, one would expect that H is normal in G. Okay, so this will take us a bit, not too much, but assume not and set. So if H is not normal in G, then I can somehow check how much not normal it is it by considering its normalizer in G, and this is not all of G. Maybe I will describe what I'm about to write down here in words before writing it, and then it will be clear. What I will do now is double the situation. I will look not on G mod H, but on G mod H times G mod H. And there is an invariant measure on that variety. This is mu times mu. Right? Mu times mu is an invariant measure on G mod H times G mod H. And I can disintegrate this one into orbits. So I can find another measure, mu prime, on a certain G orbit for the diagonal G action on G mod H times G mod H. Now, what is the stabilizer of an orbit in G mod H times G mod H? What is the stabilizer of a point in the product space? it's the intersection of two stabilizers. So the stabilizer of mu prime will be the intersection of two conjugates of H. Intersection of two conjugates of H is smaller. And this can't happen unless something trivial is happening. So it can't happen by the minimality of H. Unless something trivial is happening, and this is that I conjugated by something which normalizes the original Earth. Maybe not a typical point, but a base point, comma, another point. The stabilizer of this will be H intersection with a conjugate of H. And this conjugate should come from the normalizer in order not to decrease the intersection. So this means that somehow mu, or mu times mu, only supports things at the n mod H, not at g mod H. But mu is fully supported. Also, mu times mu is fully supported on g mod H times g mod H, and I will get a contradiction here. So this is the general idea, and now just I have to write it down. So be prepared for details, but this is the thing. So now I want to basically I want to define the generic set of points in g mod H times g mod H for which the stabilizer is smaller than H, or smaller than H after conjugation. This is a generic, this is the Zariski dense, sorry, the Zariski open subset. This is a generic condition. So this is what I'm arguing. Consider the following map here. X, Y is not Y equals X. And now I'm defining U inside again. I want U to be the set in G mod H times G mod H such that the stabilizer and the diagonal action are small. And this will be a generic, an open Zariski set. So let U be the image of inside here I have N, which is not everything. It's a closed sub. I phi inverse into here. Or actually I take the complement, which is open. I phi inverse it to here, and this is this set. And I'm taking this open set of G times G, open non-empty set, and the open map, and I'm taking the open map from G times G to G mod H times G mod H. I think this is something I did not say, but the map from G to G mod H is open. I should have written it when stating Chevalier's theorem of coset spaces. So this map is open, and this is open in here, and I push it here, and this, and the image will be U. Okay? Now we should check that if I'm having an element in U, in this open set, or maybe U is the summary, an open, non-empty set. It's non-emptiness, which is equivalent to this, which I'm about to contradict. I'm about to get a contradiction. I'm under the assumed not hypothesis. Okay, we take a point here, and the fact that this point is here, if you just read back, it's exactly saying that y inverse x is not in. And this says that the stabilizer in G of this U point, well, which is now I'm writing, just identify this. We know, I already said it, this is intersection of two conjugation of H. And maybe just to make it clear, I want to write it in the following form. This fact means if you check, this is not in the normalizer, so this group is not H itself. And the intersection is much smaller. It is strictly smaller. And since I have this y, it is smaller than Hy itself. Now I'm doing this doubling trick. Consider mu times mu, which is a measure on G mod H times G mod H, and it is L invariant. And first of all, I want to observe this is fully supported. Now, when I will discuss supports, most of the time I will discuss Zariski support. So if you know the definition of a support, the Zariski support will be the Zariski closure of the usual support. I'll write it specifically. I'm looking at the support of mu times mu in this space, and the Zariski closure of this. Now, what is the support of mu? Maybe this guy. First of all, is L times L invariant set. Z closed. So the support of mu on G mod H is some L invariant set, since mu is L invariant. Support of mu times support of mu is L times L invariant set on G mod H times G mod H. The Zariski closure is still L invariant, and it is a Zariski closed set. Hence, it is L times L Zariski closure, and this is G times G invariant. That is, there is only one non-empty G times G invariant set in this G times G homogeneous space. That is the support of mu times mu, so it's a closure. The support is Zariski dense. Right? We check that the support is Zariski dense, and this means that our Zariski open set U has non-trivial measure. It can't be that the support of mu times mu is contained in the complement of U, because the complement of mu is Zariski closed. The Zariski closure of it will not see mu. We will not see U. Now this implies some disintegration measure of mu with respect to take this variety, mod G out. Mu is a measure here, and it disintegrates over here to measure supports on fibers.
You
On
mean
orbit.
just square of mu, right? This increment.
Oh, sorry, mu times mu is a measure here. It's disintegrate over this space into measure supports on fibers, that is on orbits. And we have this integration formula, I will not write it again, but to measure things with respect to mu times mu is the same as to measure things with respect to disintegrated measures and then integrate further over the base. It can't be that all the disintegrated measures miss you entirely. One of them will have, a big portion of them, will have to see you, right? So now I'm picking one. Some disintegration measure of mu, let's call it mu prime, call it, or pick such, mu prime. Just about organization, we're in the middle of proving something. We now prove the claim. I will finish the claim. I will not finish the proof, and then we'll have a break, right? So let's remind what we're doing though. We are proving that H is normal in G. When H was a chosen minimal element of group of subgroups of G, such that the relevant cosec space supports an L-invariant measure. Right? And at this point of the proof, we came to consider mu prime, which is supported on an orbit. An orbit in U. U is a G-invariant set. Mu prime is supported on a single orbit. This is how disintegrated measures look like. G mod H prime in U. But for points in U, and this is this calculation that we had on the bottom of that board over there, but for points of U, stabs up to conjugation are smaller than H, are strictly smaller than H. This is a conclusion. So mu prime, we achieved a measure mu prime, which is supported on an orbit with stabilizer, again, up to conjugation. I can look at, not at this stabilizer, but at the Y conjugate of it. And this is a point, and this gives me a point which is smaller than H, which does support an invariant measure mu prime, contradicting the choice of this minimal element H. Reading back, I did prove that H is normal in the Zariski closure of L in G. Okay? I'm quite close to prove the proposition in a whole. Do you want me to finish now or take a short break? It's a 5-minute matter. But maybe we need to breathe fresh air. Finish. Break. Okay, so let's take the proposition. G is an algebraic group, which I'm assuming it's a Zariski closure of L. Oh, don't be mad at me.
Some people speak not, it's hard to understand some people.
You want? We need break?
Not you.
Not me. We need a break? We need a vote? Let's take a break. I need a break, okay?